Welcome to the Deep Dive. This deep dive is sponsored by Stonefly, a leader in enterprise storage, backup and disaster recovery, AI storage, and cloud solutions. If you're looking for secure, ransomware-proof storage, then Stonefly sells air-gapped and immutable storage. Contact sales at stonefly.com to schedule a demo. Welcome back for another deep dive. Today, we're plunging into the really fascinating and, frankly, constantly changing world of Linux security, particularly how it impacts, well, the billions of connected devices out there, the Internet of Things.
Right.
You probably don't give much thought to the OS running your, smart thermostat or that security camera. But figuring out how these things can get compromised, it's absolutely critical today.
It really is. Linux is just everywhere in IoT. And look, there are good reasons. It's flexible. It works well with other systems.
Interoperability, yeah.
Exactly. And often the cloud systems managing these IoT setups are Linux-based too. But yeah, that popularity makes it a huge target.
A big bullseye.
Pretty much. And what we're looking at today really drives that home. Attackers are always finding new ways, clever ways to get in and, importantly, to stay in these systems.
Right. Persistence.
Yeah.
So, okay, our mission today. Let's unpack how attackers exploit some common Linux system features.
Yeah.
Look at a really cutting-edge example of a new threat aimed squarely at IoT.
PumaBot.
And then explore what you can actually do about it. How to defend against these attacks. Should be some aha moments, I think. Okay, let's unpack this.
Right. So let's start with the basics, the foundation. Linux and IoT. It's ubiquitous. Simple sensors, complex industrial controls, surveillance systems.
It's the engine under the hood.
It's the workhorse, yeah. And a really key part of that engine, especially in, modern Linux distributions, is something called system.
Ah, system.
Yeah.
Okay, I've definitely seen that mentioned. What exactly is its job?
So think of it as the main system and service manager. When your Linux device boots up, systemed is like one of the very first processes to run, PID1, usually. And its main job is just to initialize the system and start all the other services and processes, daemons, that the system needs to actually function properly. It manages all this based on these configuration files. They're called service unit files.
Unit files. So these are like instruction manuals telling system what programs or scripts need to run and maybe when.
Exactly that. They're just plain text files, usually. They have different sections, like unit gives a description, service is the important one. It specifies how to run the service.
Like the actual command.
Yeah, the command to execute exec start, commands to run before or after exec start, pre-exec stop, options, that kind of thing. And then there's install.
Okay, install.
That tells system how the service fits into the boot process, like when should it start. It often uses targets, which kind of replaced the old run levels.
So you could tell it, hey, run this service every single time the system boots up.
Precisely. You'll often see wanted by default.target in that install section. That basically means start this service when the system reaches its normal multi-user state. And these files, they live in standard places, typically at system for system-wide services.
Okay, I see where this is going from a security angle.
Yeah.
If these files tell the system what critical things to run at boot, that sounds like a perfect place for an attacker to hide something malicious, doesn't it?
It's an absolutely prime target. The materials we looked at call system services an awesome artifact for attackers who want persistence.
Awesome for them, maybe not for us.
Right. If an attacker manages to get enough privileges, usually they need root access for system services. They can just create their own malicious service unit file.
That's right, they're a little instruction file.
Yep. They write the file, configure the service section to run their malware payload using exec start, drop that file into, say, acceptive system.
Hiding it among the legit ones.
Exactly. And then they just need to tell system about it. They use the command system ladle enable name, where name is the name of their malicious service file. That command creates the necessary links so it starts automatically on the next boot.
And they can probably start it immediately too, right? Without waiting for a reboot.
Oh, yeah. System 6 will start name will kick it off right away. So it's straightforward, relatively easy if you have the permissions, but incredibly effective for ensuring their code survives reboots.
Wow. Okay, is this theoretical, or are attackers actually doing this out there?
Oh, it's very much real world. We've seen it quite a bit. There was an incident back in 2018. An orphaned package in Arch Linux got compromised.
Right, I remember hearing about that.
Yeah, the malicious script dropped in there used systemed for persistence. There's a threat actor known as ROC. They often use system services to make sure their payloads, often written in GoLang, execute on boot.
GoLang again.
Yep. And even, standard offensive security tools like the Metasploit framework added modules to automate creating malicious system services years ago. It's a well-established technique.
So if you're looking at running processes, normally a legit service started this way would have system PID1 as its parent.
That's the typical process hierarchy, yes.
Okay.
Systemed is the ultimate ancestor for most system services it launches. So if you're investigating and you see something suspicious, maybe like a shell script, bash, Python, running, and its direct parent is systemed, PID1, that's a strong indicator.
A red flag.
A definite red flag. It strongly suggests it was launched via a system service unit file's exec start command. Now, it might be legit, some custom admins group maybe, but it definitely warrants a closer look. You'd want to find that unit file and see what it's doing.
Right. Okay, speaking of evolving techniques and attackers getting clever, let's talk about this new threat that ties some of these ideas together, PumaBot.
Yeah, PumaBot. This is a pretty recent discovery, actually. It's a botnet written in the Go programming language.
GoLang seems to be everywhere in malware lately. Why is that?
Well, it has a few advantages for malware authors. One big one is cross-compilation. You can write the code once and easily compile native binaries for Windows, Mac OS, and Linux. That's efficient.
One code base, multiple targets.
Exactly. And it also tends to bundle libraries statically. This means the resulting binary is often self-contained, doesn't rely on external libraries being present on the target system. This can sometimes make the binaries larger, which isn't always great for stealth, but it can occasionally make it harder for some maybe older signature-based security tools to pick up on reused malicious library code. Plus, no messy runtime dependencies left behind.
Interesting trade-offs. Okay, so PumaBot, written in Go. How does it actually get onto these Linux IoT devices?
Its main way in, based on the analysis we have, is good old-fashioned brute-forcing SSH credentials.
It's hammering away at passwords.
Pretty much. But it's slightly more targeted than just random scanning across the whole internet. It seems to get a list of potential target IP addresses, ones with SSH ports open, directly from its command and control server, the C2.
So it gets a hit list first? Smarter.
A bit smarter, yeah. And interestingly, during the brute force process, it apparently includes some checks. It looks for specific system strings.
Like what?
Like Pumatronics. That's a known manufacturer of surveillance cameras. This might suggest it's specifically targeting certain types of devices, or maybe even trying to avoid certain environments, perhaps honeypots that don't match expected profiles.
Huh. Okay, so it gets in via SSH brute force. What's its next move?
Once it's in, the goals are pretty standard for this kind of malware. Establish persistence so it survives reboots, and then execute malicious commands from the C2. First thing it does is gather some basic system info on name, output, kernel version, that sort of thing, and phones it home to the C2.
Reporting for duty.
Right. And sometimes it uses a custom HTTP header for this communication. The analysis noted one like X API key Jiridashabi. Seeing unusual headers like that in network traffic is another potential indicator.
Good tip. Okay, persistence. How does PumaBot make sure it sticks around? Does it use systems like we just discussed?
It absolutely does. It employs a couple of tricks. First, it tries to disguise itself. It copies its main executable binary to a location like libradis.
Libradis. Trying to look like part of the Redis system.
Seems like it, yeah. Hiding in plain sight, or trying to. Then it creates a persistent system service unit file, dropping it into the usual STIC system directory.
And what does it call the service?
This is where it gets sneaky. It names the service file either redis.service, matching where it put the binary, or mysqI.service.
Wait, mysqL, but with a capital I instead of an L.
Exactly. mysqI.service. It looks almost identical to the legitimate mysqL.service at a quick glance. It's a classic typo squatting kind of trick designed to fool a casual inspection.
That is devious. Very clever.
It is. And that's not all for persistence. As an extra backup, it also adds its own SSH public key into the authorized keys file for the user account it compromised.
Ah, so even if someone finds and deletes the dodgy system service,
the attackers still have SSH access back into the box using their key. It provides redundancy.
Multiple footholds. Okay, so it's in, it's hidden, it's persistent. What's the actual payload? What damage does it do?
Well, its primary observed activity seems to be cryptomining. It tries to run miners like xnrig to use the device's CPU cycles to generate cryptocurrency for the attackers.
Right, turning the IoT device into a zombie miner.
Pretty much. But it doesn't stop there. It actually downloads and runs a whole chain of other malicious binaries to expand its capabilities.
A whole tool chain, like what else?
Yeah, the analysis found several components. There's a backdoor binary called daemon, another separate SSH brute forcing tool named networkexum, presumably to find more victims from the already compromised device.
Sledding the infection.
Exactly. There are also some shell scripts involved, like installx.sh and jc.sh, probably for setup or other tasks. And then there's a really nasty piece, a malicious pemunix.so file.
Pamunex.z. PAM is pluggable authentication modules, right? For login stuff.
You got it. PMIN is the standard Linux framework for handling authentication, logging in, changing passwords, all that. Pamunix.so is the normal, legitimate module used for authenticating users against the local password database, etc., shadow, etc.
So what does the malicious version do?
This malicious Pamunix.so deployed by PumaBot acts as a rootkit, specifically targeting credentials. When any user successfully authenticates, say, via SSH or even a local console login, this rogue module intercepts the process after the system validates the password but before it grants the session. It grabs the username and the clear text password.
Whoa, clear text password.
Clear text password. And it writes these stolen credentials to a file, typically hidden away somewhere, like us.bincon.txt.
Wow. So it's not just brute forcing to get in, it's actively stealing the credentials of legitimate users after they log in. That bypasses watching for failed logins entirely.
Exactly. It's a much stealthier way to harvest credentials. And then there's another binary in the toolchain simply named 1.
Just one.
Yep, just one. This binary's job is apparently to monitor that us.bincon.txt file where the credentials get dumped. When new credentials appear, 1 reads them, sends them off to the C2 server.
Exfiltrates the stolen passwords.
Correct. And then it deletes the us.bincon.txt file to clean up the evidence. And of course, this one binary also needs to persist, so it sets up its own system service, usually called something like mydemon.service. It's a whole interconnected system of malware.
Man, that PumaBot sounds like a potent cocktail.
Yeah.
Leveraging core system features like systemed in PAM, brute forcing, credential theft, crypto mining. How does this specific example fit into the bigger picture of threats facing the Internet of Things?
Well, PumaBot really exemplifies a couple of major converging threats we're seeing. First, obviously, the continued rise of IoT botnets. Attackers compromise these vast numbers of connected devices.
Cameras, routers, smart appliances.
All that stuff, yeah. And they corral them into these huge networks, botnets, to launch attacks. The classic use case is distributed denial of service, DDoS, just flooding targets with junk traffic.
But we've heard DDoS isn't always the main goal, right? Sometimes it's a smokescreen.
It absolutely can be. They might launch a noisy DDoS attack to distract the security team while quietly in the background they're installing other malware for data exfiltration or maybe setting up for cryptojacking like PumaBot does. And newer botnets are getting smarter too, moving beyond just raw traffic volume to exploit application-level weaknesses or even mimic human behavior to get past defenses.
And PumaBot clearly ties into that cryptojacking trend as well.
Definitely. Cryptojacking is where malware hijacks the device's processing power, its CPU, sometimes its GPU if it has one, to mine cryptocurrency for the attacker. It often runs hidden in the background. You might notice your device is slower, or maybe the battery drains faster, or your electricity bill goes up.
Subtle signs.
Can be subtle, yeah.
Right.
It causes performance issues, wastes energy. We've seen other campaigns focus heavily on this, like one called Redis Raider that specifically targeted vulnerable Redis servers, which PumaBot also seems interested in mimicking.
So PumaBot is kind of doing double duty, using the compromised IoT device's resources to mine crypto for profit, and also using it via that networkexum tool as a platform to brute force SSH on new potential victims to grow the botnet.
That seems to be the model, yes.
Yeah.
It's efficient for the attacker. The compromised device generates revenue through mining and helps expand the operation. And the sheer scale of IoT, billions of devices, many with weak default passwords or known vulnerabilities, just creates this massive, constantly growing attack surface. They're very attractive targets.
Okay, so with threats like PumaBot out there, combining all these techniques, how can you actually defend your Linux-based IoT devices or even just regular Linux systems?
It really has to be a proactive, continuous effort. The old set it and forget it approach for deployed devices just doesn't cut it anymore.
Fire and forget is over.
Definitely over. Security has to be baked in and then maintained over the entire life of the device. A huge part of that is, first, really understanding the system internals. Knowing how systems works, where service files are supposed to live, what normal processes look like.
Oh, my system.
Exactly, because you need that baseline to spot anomalies. What kind of anomalies? Well, based on PumaBot's tactics.
Right. What should you look for?
You'd want to monitor SSH login activity closely. Are you seeing tons of failed attempts? Are there successful logins from IPs you don't recognize? That could be brute forcing. You need to regularly audit your system services.
Look for those weird names like mysqI.service.
Yes. Look for suspicious names, type of squatting like that, or services pointing to executables in weird places like libredis. Also, check the authorized keys files in user home directories. Do you recognize all the public keys listed there?
Good point. Easy to overlook.
Very easy. Monitor file integrity in critical directories like etsystem. Are unexpected files appearing or changing? And then network traffic monitoring is key. Are devices making unusual outbound connections? Is there traffic using cryptomining protocols like Stratum? Are you seeing strange HTTP headers like that XAPIQ example?
That sounds like a lot of things to keep track of, especially manually.
It is. It's a significant amount of work, which is why automation is becoming so crucial. Tools like network detection and response, NDR, or advanced endpoint security solutions, EDR/XDR, many of these use machine learning or behavioral analysis to learn what's normal for your network and endpoints, and then flag suspicious deviations like these automatically.
So leveraging smarter tools.
Leveraging smarter tools, absolutely. And beyond tools, having a structured process for handling threats is vital. The materials outlined a good four-step cycle. Monitor intelligence sources for new vulnerability reports and threats. Assess if your systems are actually affected and how badly. Notify the relevant stakeholders, your teams, maybe customers if needed. And remediate apply patches. Implement workarounds. Block malicious IPs. Do it quickly.
Monitor, assess, notify, remediate. Makes sense.
It does, but actually implementing that cycle effectively in-house, especially if you're managing thousands, maybe millions of deployed IoT devices, it's incredibly resource intensive.
Yeah, I can imagine.
Just the cost for experienced security engineers dedicated solely to tracking CVEs and threat intelligence could easily hit $500,000 a year or more just for that one function. That's why, honestly, for many organizations, partnering with specialized security vendors often makes more sense.
Because they do this at scale.
Exactly. They have the dedicated teams, the threat feeds, the automation, the cross-industry visibility. They can often detect and help remediate these things faster and more cost-effectively than trying to build and maintain that capability entirely yourself. So yeah, to kind of bring it all together, Linux is powering more and more IoT devices, which makes understanding Linux security vital. Sophisticated threats like PumaBot show how attackers are creatively abusing core system features like System for Persistence, PM for credential theft, and combining them with crypto mining and botnet mechanics.
It really is a constant arms race, isn't it? Attackers find a new trick, defenders figure out how to block it, attackers adapt.
It absolutely is. And securing these devices, it's not a one-and-done task. It's this ongoing cycle of vigilance, monitoring, detecting anomalies quickly, and having a solid plan to respond. Knowing your systems, knowing what normal looks like, that's fundamental because that's how you spot the abnormal, the malicious.
And the stakes are just getting higher, right? It's not just about someone's smart toaster anymore. It's critical infrastructure, industrial systems, government networks relying on these connected devices. It really makes you wonder, looking ahead, with AI becoming more powerful, is it going to empower the attackers more, helping them create even stealthier, more adaptive malware? Or will it give the defenders the edge with faster, more accurate detection and response? Definitely something to think about. This deep dive was brought to you by Stonefly, a leader in enterprise storage, backup, and disaster recovery, AI storage, and cloud solutions. If you're looking for secure, ransomware-proof storage, then Stonefly sells air-gapped and immutable storage. Contact sales at stonefly.com to schedule a demo.